Okay, quick new concept. They're talking about structural isomers here, and this isn't too bad. Let me just give you a quick sketch of what those are about. Structural isomers are two chemical species that have the same formula. You can't tell them apart by their formula. The only thing different about them is their structure, the shape of the molecule. So, for example, here I have but1-ene and but2-ene. If you wrote just the atomic formulae for these, they would both be C4H8. Just looking at that, you cannot tell that they are different. But if you look at their structures, this one has a double bond on the end, this one has a double bond on the middle, and that can make a difference to how polar they are, what their melting and boiling points are, how reactive they are. All kinds of stuff can change just from the structure being different. So the point is, you cannot tell these things apart, or there's a lot of important information that is lost if all you give is this atomic formula. And so structural isomers are chemicals where you have to watch it because they have the same formula, but they're not shaped the same. So if they're looking for which of these are structural isomers, we have to figure out what are the atomic formulae for all of these, and we're wondering if any of them will match. Let's find out. So what this means is we have to get this molecule into a state where we can count carbons and hydrogens and see what its atomic formula would be. This thing means we have a carbon, 3 carbons in a triangle. That's what this means. And then we have another CH3 sticking out on the end here. Now, how much hydrogen have we got on these other things? 1 there, 2 here, and 2 here. That means this molecule overall has 4 carbons and 1, 2, 3, 4, 5, 6, 7, 8. Heh. That's funny. I didn't even plan for this to happen, but this thing is an isomer of those two examples I gave at first. I did but1-ene and but2-ene. This thing happens to also be C4H8, so this is an isomer with both of my examples. The question is it an isomer with any of these other molecules? We'll soon find out. Echoes there. We found that this is C4H8. What about butane? This one's nice. They already did the hydrogens for us. So this has 1, 2, 3, 4 carbons. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogen. Not a match. These two are not isomers, but the search continues. This is another nice one where they did the hydrogen count for us. So 1, 2, 3, 4 carbons. And then hydrogen 1, 2, 3, 4, 5, 6, 7, 8. So there's a hit. Methyl cyclopropane and but2-ene are structural isomers. You can't tell them apart from this formula, but you certainly can once you draw the molecule. The shapes are all different. What's going on with this last one? This is cyclopropane. That's a solid line. I'll explain what those lines are about at the end, but for now, let's suffice to say that that's a bond like all the others. So what is this shaped like? We got a carbon, a carbon, a carbon in a ring, and then we have that coming off the tail end. Well, I'll end the suspense quickly. This has 5 carbons in it, so it's C5H. Who cares? It's not going to match any of the others. So the only ones which are isomers, or isomeric, are these two. They have a matching formula, but not the same molecular shape. Now, in case you were wondering about how they drew this structure and maybe this one over here, there are some tricks that they use to try to represent 3D a little bit better when they're drawing a molecular diagram on a flat piece of paper. And what they do is, if you're drawing something that's in the plane of the paper, you just draw it as a simple line. That means flat. If a line is supposed to be coming out of the paper at you, they draw it like this, like a wedge. And this is supposed to mean the fat end is closer to you, and this end is further away. It's supposed to look like, imagine someone's holding a ruler way far away and they're poking it at your eye. So this end is supposed to be nearer to you, coming out of the paper, and this back end is supposed to be farther away. And so that's for things that are coming out of the paper at you. The other thing that can happen is you can have a line that's disappearing back into the paper, like it's moving away from you. And for those, they draw a dotted line. And that means like receding. I suppose they could use this again, only pointed the opposite direction, but instead they chose fading back away. So in this diagram, what they're trying to draw is that this line is flat. These two lines are coming at you. So it's like you have a triangle that's lying down. This line is further away. This line is coming out at you. And so is this one. It's like you're looking at a piece of pie with the point aimed at your face. So this point is supposed to be nearer to you than either of these, and they show that by making those lines get thicker at the end. For this molecule, this line is flat. That one's right in the paper. This one is supposed to be coming out at you, and then this one is fading back. So that line is supposed to be sticking up out of the page, and then this one is going back down to the level of the page. Tricky to visualize, but that's what those are for. We're not going to get into how to draw them, but you will see them occasionally in molecular diagrams, and that's all they are. It is not critical to interpret those right now. Just know that you can replace those with regular old lines anytime you want to, like I did here.